educational career that is important. Should I repeat it? I saw that you've just switched on the recording.
Oh, I forgot. I think we're probably okay. You can start again if you like.
Fair enough. Fair enough. All right. So already early on in, I guess at some point in the primary, they tell us that solving systems of equations is quite important. And I think it's a bit underdeveloped area of quantum chemistry when it comes to the application of quantum algorithms. There are not that many publications on using the quantum speedup algorithms for this problem. And that's what we're going to discuss today. In particular, we're going to be looking at the paper of the group from, let me just see it exactly so I don't. We're going to be looking at the paper adapting the HHL algorithm to non-unitary quantum many-body theory. And just so I roughly know, how many people have heard about HHL? Could I have the show of hands? All right, some hands are up. All right, but let me go through it nonetheless. So in the primary, they tell us about this classical linear system problem, which could be classified as follows. Let me divide it. As the input, we're given some matrix. In the primary, it's not necessarily with complex entries, but here we can actually use it. And some vector B, also with complex entries. And what we are after is a vector X, also with n complex entries, such that it satisfies the following equation. Or we want the information that there are no solutions. And since we want to be quantum really requires us to reframe this problem for the quantum setting. We will be talking about the quantum states, because that's what we are dealing with in quantum computers. So similarly, we've got some input, and this is a matrix A, also with complex entries that we can access via an oracle.
Yeah.
Likewise, we are given vector B, and and now our goal is to output a state X. I'll put a little tilde with it just to imply that this is an approximation such that the distance between the output and the actual solution to let me also define vector X is such that after the inversion of A and multiplication by B, we get that vector. So the output is some approximation of this X encoded as a quantum state such that the distance between the two, so our precision is less than some epsilon And we want to get that with the probability higher than 1/2. Or similarly, we want to get information that there are no solutions. And here is a little aside. Normally, the HHL algorithm is framed in such a way as to remove this possibility, because this is not too nice to include and would make us consider some additional cases. So we say that the trace of A is equal to 1. And this ensures that A is actually invertible and we can deal with the problem. All right, so on the left-hand side, we've got the problem that we're familiar with. It's fairly normal to get it in some calculations, let's say, of energy levels in quantum chemistry. And we've got the quantum restatement. And B and X are quantum states that are, actually, I could even write it like that. These are normalized quantum states. Right. And my idea to present this is to show you the circuit of HHL. It's really quantum phase estimation with some conditional rotation, and the rest of it is the housekeeping and cleaning up, I'd say. So let me draw it. We'll be dealing with 3 sets of components. Right. We've got the ancilla register. That we initialize in 0. We've got the clock register. I hope it's legible.
Yeah.
Cool. And this is some tensor product of n ground states and also the input state. Right. What we are starting with is the phase estimation. I realize I don't have an eraser in here, or at least I can't see it. So we will be dealing with it like this. So yeah, first of all, we've got the clock register. We put it into some superposition of states. So we apply Hadamard and n-dimensional Hadamard. Then we actually do the evolution of the Hamiltonian, or the situation that we want to deal with, conditioned on these. And we finish off with the Fourier transform, with the inverse Fourier transform. So
Can I check
after
that
this,
Hadamard
yeah,
is just 0 states and all the 1 states? Is that the sum of those?
yes, so we've got n ground states, and we apply a Hadamard to every one of them.
But is it sum of 2? So they're independent Hadamards, or is it a single Hadamard that gives you a superposition of all the zeros and all of the ones?
Yes.
Okay, fine. Okay.
Mm-hmm. Yeah. So yeah, that's correct. And we've got the so overall, this is the phase estimation state. Right, now we apply some rotation conditioned on the clock register. And after that, what this So let me write it. What this step does is to take the eigenvalue that we eigenvalue of the Hamiltonian operator, which in this case is equivalent through some manipulation to the phase that we've just got. Is the point of this step is to take that from the quantum state into some coefficient that later in the long term we will be able to measure in the ancillary register some coefficient. And then
Okay.
the final step.
Can I just check what you mean by that? So at the end of the phase estimation, you end up with your eigenvalues written into the state of the clock register. So then you're trying to move that into an amplitude on the ancilla qubit instead.
Yes, so maybe I'll write it down here. So let lambda be this phase that we're estimating, not really the phase, the eigenvalue. So after the phase estimation state, we've got the following. So in this step, we estimated the eigenvalue, and it's within the state, whereas after the rotation, what we really want to get is the following. Lambda j uj 0
So is this
plus.
So after the phase estimation, you have essentially a bit string for your lambda j, which is the binary representation of that eigenvalue.
This is some approximation, and then we want to turn it into a coefficient in this linear combination of states.
Wouldn't you just be able to, if you had started with uj, wouldn't you just be able to measure the clock register and you'd get lambda j out immediately without having to write it into an amplitude?
Well, but that would be just for one state, whereas we want for one component of the state, whereas what we want to get is the same information for the entire state X.
Okay.
So
What
this is a good observation. Yeah.
What does the control gate there look like? What's it indexed on?
This control.
Yeah.
This is control. The control qubit is the clock register.
So you need a control for every single bit string on that register.
Yes. And what I'm doing here is just to show one of them.
Okay.
So let me finish writing this. Uj. So we're just completing it. All right, so we've estimated the eigenvalues, then we made the controlled rotation to get the eigenvalues out of the state, and in the long run we'll measure for 1 to get something 1 over the eigenvalues, and hence we get the value that we are after. And really what is left is just tidying up. So we're mirroring the phase estimation to uncompute this part.
Could I ask what C is? Is that just to
C-
be sure it's normalized?
C is just a constant to normalize it.
Okay.
Well, where does
So-
the rotation value come from?
Sorry.
The rotation, that controlled rotation,
Mm-hmm.
I can know what to rotate it by.
This is achieved by Pauli Y operators. So what we rotate here is really this. By how much we rotate is the following. And this obviously is under the assumption that we have no error. Obviously, I've lost my, here it is. This obviously is the perfect case. We may get some phase or something else. So this step is not necessarily ideal.
How do you do that rotation without knowing what lambda J is? So you're rotating in the subspace, the insular subspace, the 0, 1 subspace. But how do you, how does the control work? Because surely you want it controlled on what lambda J is, but you don't know what lambda J is.
Or is it a set of, I don't know, some horrible binary tree of rotations that's encoded by the binary form of the clock register?
Yeah, I think
Is that something like that?
Yes, exactly.
Okay, so if each of the binary bits of your clock register controls a set of another rotation of increasing size. Factor two. Yeah.
Right.
So it's a slightly horrible gate.
Okay.
Yes.
It's if you don't have a
Yeah.
rotation by divide by two.
Yeah.
In a binary representation.
Oh, I see. Okay.
Divided by 2 is just all the fixed point.
Fixed point, so you represent it as function two.
Yeah.
Right?
But
Okay.
each bit string, you get the whole like precision spectrum.
Yeah.
From like it's not just balanced to it, so you get the in between precisions as well, right?
Mhm.
It's, you divide by 2, but then you can get like 5/4, for example. So 3/4 by having
Three
it.
quarters is a quarter plus a half.
Yeah,
Yes.
Yeah, by
Yeah.
doing successfully.
It's a basis that's unique.
Yeah. Okay, that makes sense. Could I also ask, so C is normalizing that expression.
Yes.
How, is that something you need to choose somewhat? Or does that will affect the rotation?
Well, eventually you can just choose it as far as I think it is this algorithm is concerned. Because after all, what you're really after is this inverse of lambdas. So C doesn't matter. It's good to, or maybe let me put it this way. Even if you don't choose it, and this is some value that you don't know, you know that your resulting X state is going to be proportional to that number, not conditioned, but it's going to be proportional to 1 over lambda. So the solution to your problem times some constant C. And this is really the weakness of HHL algorithm. One can't really it's not getting the real solution to the linear system of equations problem. What you can do with this value, you can really just shuffle it into a new function that you have to evaluate for some reason. That is, let's say, multivariate or has as the input these numbers corresponding to vector x. That's the weakness of the algorithm. Right, so let me just finish. As I said, we're just uncomputing. And what we're left with is the following. Oh, it's gone away. Yes. So now to access these precious informations that we've worked so hard to get, we're measuring in the ancillary register to get 1, just because it's easier to access it than the square root. Here we're back to the starting state, and here we get x. Right. I can go into the details of the algorithm if you've got some questions. So there are certain restrictions on what sort of matrices this particular statement of the algorithm can admit. Well, the best way to see what the restrictions are is by comparing the complexities. So classically, solving this problem, let me just see, right. Classically, solving this problem can be done by the conjugate gradient method. And in that case, the complexity is as follows. It's O of NS kappa logarithm of 1 over epsilon. And N is the size of the system. S is the sparsity of the matrix. Kappa is the condition number.
It's the ratio of the highest and lowest eigenvalues.
Magnitude of them.
Sorry, Alex, what did you ask?
That's the ratio of the magnitudes of the highest and lowest eigenvalues of A, is it?
Exactly.
Spectral then.
Good.
And epsilon. Oh, sorry. Yeah. Yeah. Sorry, sometimes I can't hear, and yeah, I'm just making sure. And epsilon is our precision.
Yeah.
So this is the classical case. And quantumly, the complexity of this version of the HHL algorithm is logarithmically better in the size of the system, but it comes at a cost. So the complexity as a function of sparsity and the condition number is linearly worse. And also the precision actually deteriorates, the complexity on precision deteriorates logarithmically. There are a few improvements to this algorithm that give advantage for certain of these parameters. For example, there is a formulation that works for dense matrices that is completely independent of S. But yeah, today we will not be covering it because I guess we don't have time, but there are certain improvements. All right. Are there any questions regarding HHL per se?
So this, the condition number in particular, how do you know what that is, depending on the application? It doesn't sound like the easiest thing to estimate, because that will affect the complexity quite a bit.
Yes. So, well, a priori, you don't know it. You just know. So you get eigenvalues through the algorithm, and then you can learn it. Also, you can just do inversion of the matrix for this problem classically. It's something like n cubed in terms of complexity, but you can do it. So if you really want to know what the complexity is for a particular case, you either run it or you just do it classically and you can say that much.
Okay.
And actually, it's a good observation because the paper that we're going to discuss today appreciates this problem, that getting eigenvalues is actually horribly difficult for certain cases. And they present a number of improvements that are supposed to change that. Right. So we can move to the paper if there are no more questions, but I was once told at training for public speakers that one has to give people 10 seconds at least to think about questions. So yeah, 10 seconds now.
So Gershwin's circle theorem, I can't remember. Would that give you an idea of what the Newton number is?
What is it? Okay. I'm not sure it would actually. It depends what the biggest eigenvalue is, but maybe Tesla will come up. Yes, it would actually. Yeah.
Okay.
Yeah.
But I can't
But
remember
the highest diagonal plus something and the lowest diagonal minus something
Okay.
would tell you, but it's a horrible bound because it could be
Okay.
negative. Yeah.
Okay.
You care if the minimum eigenvalue is very small, close to 0, and the circle theorem will probably give you a negative number as the lower bound for it.
Okay.
Probably.
Right.
Yeah. So
So
it's probably not helpful.
Yeah. Okay.
Yeah.
All right.
I think
Let's.
yeah.
Yeah, I think this has been enough. Let's move to the paper per se. And I remember once, I think it was you, Alex, at some point you, after one of the discussions, you asked us, so what's going to happen to this paper? Is it going to be published? Is it going to be stuck in an archive forever? And I would like you all to do a similar thing with this paper. I'd like to hear your opinion after we discuss it, because from the application point of view, they advertise to us some software that they can run on real hardware. If I'm not mistaken, they used IonQ software, IonQ hardware, sorry. And this is something that researchers around the world could use, especially given the performance. So this table, in particular parts D, E, and F, show you the reduction. These are these numbers. Oh, let me switch that on. So these numbers.
Can you zoom in a little bit?
Sure.
One more? Yeah.
Right. Right. So these numbers show the reduction of well, I'd like to move it there. Right. All right. The scale bar. Sorry, my computer's messing up with me. Right. These numbers show the reduction in the resources needed to do certain molecular calculations. So what they do in here, they calculate certain energies for molecules like H2, H3+, lithium, for these molecules, hydrofluidic acid, and so on and so on. And these are and this is the reduction in the resources needed. And one important figure of merit that they use is the value, how far away from the actual values they are, PFD. And that you can see from the scale bar. So at the cost of reduction, reducing the resources by half, one can still get the results that are just 10% off from the actual value. And this is the worst case scenario that they perform, that they report. For example, here, the performance, I know from the scale bar, I guess it's something like 2%, 45% reduction of the resources needed, and still pretty decent result. So what we're going to do is to discuss these different adaptations of HHL, like perturbed HHL, adapt HHL light, and some others that they mention. And we're going to discuss them, and they say, well, we can actually run it on real hardware today and still get, to my liking, quite decent results. So yeah, just bear my question in mind for the end. I would really like to hear your opinion on whether this is actually useful or it is just some theoretical discussion that won't be really useful to anyone for some time. Right. Have you had the chance to glance the paper?
Assume not.
Sure. That's what I was going to assume, but it's always good to ask.
Yeah.
Right. So let's start from the beginning. So obviously the authors say that so far we've been using quantum computing for quantum chemistries to evaluate certain energies, be it through quantum phase estimation or variational quantum eigensolvers and similar algorithms. But obviously there are some problems that the authors indicate, like the rapid increase of circuit repetitions in order to suppress the effect of short noises on the calculations that we do. And also difficulties associated with the variational optimization of parameters. And what they suggest is the application of the HHL algorithm to the problem of solving the equations describing linearized coupled cluster. And in this particular paper, they're concerned with the calculation of correlation energies of some light molecular systems as the ones reported in the paper.
I'd say significant precision is a very nebulous word.
Yes. Yes. Well, depends what you're using it for. If yeah, and how quickly one needs it. Yes, and another advertisement that the authors make is that somehow, not somehow, oftentimes we have to deal with non-unitary operators, and they actually want to track that problem. What they also advertise the paper for is the resource reduction, and they argue that in the NISQ era of quantum computing, we're painfully limited by the number of and also the quality of qubits available. But they obviously say, well, for now we've got these trade-offs that you'll see in our paper, but gradually they hope for the increase of quantum resources. And what I'd like to draw your attention to is actually what Chiara already said. I'm looking for this part. That is actually sometimes costly, or even more often than so, to get the eigenvalues of the matrix. And therefore, they propose this X module that is designed to address this issue. So they want to do calculations without the estimation of or the calculation of the eigenvalues which to me is, I can see plenty of potential for that. And they do that by studying the distribution of eigenvalues from the quantum phase estimation in order to reduce the number of gates needed to do some calculations. So that's one problem that they are addressing. Another problem is that they want to optimize it, this particular scheme for quite small quantum computers. That's the reason they deal with multi-qubit fixing, conditionally on some probability threshold. This is just some figure of merit that they're going to use and say that, all right, this probability is going to describe our precision, and obviously one can vary it. I do have to say that the authors throughout the paper are very cautious. They say, well, these are the numbers that we got for this particular problem. There is plenty of playing around that one can do and get different results. And also, they want to achieve single shot measurements. They just say that is more efficient, and yeah, it's hard to argue with them on that point. And as I've shown you, they calculate the correlation energies for several small molecules. Oh, and here it is. That's the information on the hardware that they were using, 11-qubit IonQ hardware to compute all of these. Right, so the problem that they deal with is the coupled cluster problem. They want to get some estimates for closed shell system, whose excitations can be described as follows with this equation. And operator T is just a sum of respective operators for n electron molecule. They say that T1 and T2 are the single and double excitation operators that produce one hole, one particle, and two hole, two particle states respectively. While this state is just the Hartree-Fock state. And here's the problem that they flagged. They said that T is actually not a unitary operator. So all the methods that they developed, they want to use for non-unitary operators. And on that part, yes. Yes, so now the important bit is the form of the equation that they actually want to solve. So for the linearized, sorry, I messed that up. For the linearized coupled cluster problem, the amplitude equations are as follows. I wasn't thinking too much about this equation, if I am honest. I haven't checked whether it's correct, but I can assume that we can assume for the sake of the discussion that it is. This is the normal ordering in this particular notation.
That EQ is normal ordered. Yeah.
Sorry?
Okay. Okay, so EQ sign phi naught gives an excited determinant in a normal ordered fashion. Yeah, okay, right. That's what it's just. Yeah. Okay.
Yes.
Probably. It was a little unclear when they talked about spin-free framework, whether they used excitation operators that were singlet, for example. They just said it was spin-free.
Yes, they actually said that spin messes up their approach. So this is quite a huge issue, but they are very upfront about that. If one is interested, one can obviously research that. But yeah, they said no spin maybe later. Right, so what they are concerned with is the calculation of these excited wave functions. So to do that, they rearrange equation, oh no, they rearrange equation 2 to the following form. And then they use the HHL algorithm for the inversion of the matrix on the left-hand side of the equation.
So it's really unclear to me whether that's a useful equation to solve. What? Number 3, or even number 2.
What's the intuition behind it? I mean,
As the linearized couple cluster. So, yeah, I mean, I wasn't entirely sure. This almost looks like a CI equation at this point, rather than, which is linearized couple cluster is configuration interaction.
Okay.
what does the linear refer to in this case? Like first order equation interaction.
Yeah, Marcel, can you just go up to equation 2 because it sort of tries to do something there. So that, yeah. So TQ is an amplitude, I think.
Yeah.
EQ is some sort of excited state, probably a slated determinant. But that then, this is therefore just this configuration interaction equation, I think, which is what you get if you linearize couple cluster. But there are people who do some linearized couple clusters that are not this.
Could you maybe check the S1 supplementary?
Well, let's assume they're doing what they're doing. I mean, if it's CI, it's CI, I suppose.
When you said linearized couple cluster, you just unroll the cluster amp, the exponential
Yeah.
operator into like the state determinant.
Okay, this feels like, yeah. That's couple cluster, yeah. And then,
So that's 6.
oh, so they create an effective Hamiltonian with the T amplitudes. Is that what this little h is then?
Could you scroll down to S6?
Mm-hmm.
Is that full Hamiltonian? That looks fine, I think, to an extent.
Right.
Just doing something. And then where's this little h come from? Amplitudes of the Hamiltonian. They've done some magic there. I don't get. Which so
Well,
if
what
you
they said,
linearized couple cluster, you might end up with couple cluster because I mean, solving couple cluster equations is an iterative thing which you could do with a series of linear problems.
Yeah.
Maybe that's what this is doing. I think it probably doesn't affect. Well, it may affect the validity of what the results are, but it probably doesn't affect what they're doing, given what they're doing at this point, and probably take too long to get to the grips of it.
Yeah, it's probably a whole for CI, all these methods as well.
Yeah, it definitely would. Okay, right. Okay, I think we'll suspend our disbelief for the moment on the operator.
fair enough.
Yeah.
All right. Well, it's not the only paper in the world where one has to trust that the authors know what they're doing.
Yeah.
Anyway, so they say that this equation is really, after some substitution, this equation which looks an awful lot like HHL, and hence they actually want to use it. And here is the mention of the spin-free assumption that you mentioned. Well, treating this problem as a matrix would be much more simpler if it was Hermitian, but this requires the excited functions forming the basis of this matrix to be orthogonal to each other.
Right. Yeah.
And they say that this, in consequence, the spin-free excitation operators need to have zero overlap within themselves, and that's the reason they say, well, not spin this time. And in general, one needs to suitably generate a new set of orthogonal excitation operators, which may be a linear combination of the non-orthogonal EPs. Right. So as we said, they are trying to calculate the correlation energy that is given by the following expression. And the final, I'm skipping a few things, but the final form for the energy that they are after is equation 6.
Yep.
And well, what follows is just the encoding of this problem as something that can be admitted to HHL. So they say that the solutions to these equations are the amplitudes encoded in the states x that we get. And as I said, HHL has this weakness that we can't really access the solutions without losing the quantum advantage. So they just work with these matrix elements.
Just looking at how they've created A, they say all the matrices are positive definite, which means they're taking minus the Hamiltonian when that minus sign indicates they're doing A is something like minus the Hamiltonian in this case.
Yes. To be honest, I'm not sure why they're doing it, but
okay.
But whatever worked for them.
They make their assumptions positive definite.
They said it happens to be in this case because of these, because the Hamiltonian, then A becomes positive definite.
Yes.
Somewhere.
Right.
Okay.
So now what they're doing, they're just using HHL to try to solve this problem. So that's something that we've already covered. They talk about the 3 quantum registers, then they apply QPE, and then they rotate the way we rotated. They do the inverse quantum estimation as before, just to uncompute this qubit. Finally, they measure and they get some probabilistic result that they trust that is correct, because, well, obviously this result is by the formulation of definition given just with the probability greater than 1/2. But where we have to get back to what they're actually doing is point 6, I think. So they say that eventually they can write the correlation energy as follows. They say that X is proportional to the solution after the measurement in the 3rd register. And now they modify. They add an additional 4th register initialized to B, which they refer to as B4. And they do it to get the overlap between these 2 states using some Hong-Mandel module. And I think looking at figure 2, that's figure 3, figure 2. It's this part that is different. And as they remark, they followed the standard HHL with a Hong model module to get the correlations of LCC framework. And this is just a compact notation for the controlled X gate, which indicates that the gate and the rotation is controlled on the ith qubit of the 4th register. with the target being the ith register of the ith qubit of the state register.
So this is just a dot product, basically, in a sort of a binary dot product.
Yes.
Yeah. Okay.
Right.
Which is what you need, indeed. Okay.
Yes. Yes.
Pairwise.
Well, it's pairwise. Sorry, yeah, they're not binary coded anymore. These are just some horrible yuck.
And the final step, by doing this this dot product, they get this expression, which is the correlation that they need.
Yeah.
All right. So that's the rough sketch of what they're doing, and for the next for what's coming, they just walk us through some improvements that help us to address the two problems that they mentioned. So the reduction of resources that they want to achieve, and also the reduction of the resources, and also trying to actually run it on the current hardware that we've got. And well, I've been talking for an hour, and is it 90 minutes or 2 hours?
90 minutes.
Hooray. So we can choose something that is particularly interesting to you, so we also have some discussion later on. They talk about some improvements here, like, for example, getting the eigenvalues from the perturbed approach. They cover multi-qubit fixing, which helps to parallelize some processes. Or they cover the pipeline-based quantum circuit optimization. If any of this sounds appealing to you, we could go through it and discuss it. So I would say please have a look for the next 5 minutes if something is particularly interesting to you in the remainder of the paper, and we can discuss it.
Can you show the circuits again?
Sure. That's the circuit. And funnily enough, they say that one of the modifications that they do helps us to not use this final module at all. So they've just created a problem because they had a solution to it. That's my feeling, but.
What is B?
So B was the initial.
Yeah.
Needed to solve for, which is
X.
so AX equals B is the thing they're solving for, and so B is that. How do the two thingies work? The two simplifications. There was something called light and adapt.
I'm not sure.
Yeah.
It must be on the unitary using the explanation.
Yeah. So Marcel, are the simplifications quite often in the QPE unitary? They're doing reducing the Hamiltonian, basically. They're applying, or.
That's one of the approach. Another of the approaches is to somehow predict or guess the spectrum of eigenvalues that they may get. What else do they do? So for example, in adapt HHL, they scale down an arbitrary symmetric posi-definitive definite matrix. So something very similar to what you said, and they just set on fetch factor that is help to somehow balance this reduction. What else do they do? In some cases, they perturb the eigenvalues, so they just if they are degenerate, they apply a level shift. So they just
Only one of
gradually.
these systems look like it should have. Actually, none of those systems look like they should have had a degenerate ground state. So do they worry? I mean, does it matter if the excited states are degenerate? Because all of those are closed shell molecules, I think.
They were. To be honest, I'm not sure. I would say that it may matter because for some reason they just restricted themselves to certain excitations, like with the spin-free approach. But yeah.
And they were just computing the ground states out of this, or were they looking at the, because this inversion problem, they could look at all of the excited states depending what you put into B.
Yes, they were looking at. Find it. Yeah. They were looking at the correlation energies in 5 different geometries.
But all at the ground state, I think. Yeah.
Mm-hmm.
Yeah.
Well, ultimately, at some point, they say that it's just the relative energy that matters, because depending on the setup of some parameters, the actual values for some estimates may largely differ, and that's the reason they do it all relative. For example, there is this probability that they use for some of the of one of the modifications that eventually is just the precision of that approach.
So they had some 2-electron systems where I think this approach should be exact, but they ended up, if you go to the end where you had that graph of the heat map, there were tables and numbers in there that were quite worryingly large. Yeah, this one.
Look at their curves. They have dimensional energy curve, and like honestly, the results are like
Which figure?
these figures. Figure 6.
Can we look at figure 6? Yeah. Yeah.
Like their error is like 2 countries,
Oh.
and it's the simulation, not the hardware.
Oh no, there's 2 times 10 minus 3. Too many hydrogens.
That's still higher than
Oh,
the
But
But like, I don't know.
And these
why
are simulated,
Actually, the simulation is so off compared to the others. I don't understand why.
So I think this is simulation, and later on they, or maybe not, this is not the simulation. I remember that there is a part of the paper where they do simulation and then they results from simulation.
Yeah.
And here are the hardware results. So let me go to that part.
Yeah, I mean, ultimately, does the hardware do its stuff well? So, I mean, I don't even know. Yeah, I don't have a feeling of how large that QPE circuit is.
Yeah, there's lots of like doing QP efficiently is like a massive field. So you can use the trotterized form of the Hamiltonian. Well, I don't actually know what the operator they're exponentiating here is. Is it the Hamiltonian?
It must be the Hamiltonian, mustn't it?
Yeah.
Or not?
or these little h.
Oh, this little h, which is
amplitude of that.
which something like a similarity transformed Hamiltonian, or
Something like
The
Yeah.
house they have.
yeah.
Was that what they referred to with this non-unitary?
Yeah, I was wondering where the non-unitary comes in. I think it's because they said something's not Hermitian.
Yeah.
Yes.
So they use the best of their circuits in supplementary.
Okay.
And for the normal HHL, it's about 2 for H2 minimal basis. Oh no, sorry, 6 for 3 1 basis. the normal HHL is 2000 depth, and the HHL light is 1000.
This is an H2.
Yes.
So
And
that's a
as
2 basis functions per atom, 631.
Yes.
So
And if you go like on lithium hydride, the depth is 42,000 for the light version.
and they managed to do what in hardware?
Yeah,
Yeah.
I don't know.
It's H2, they said. Okay.
But they don't have points for.
It's 6G. Okay, so sigma G, sigma U. This must be exact, it sounds fancy. I mean, there's only one connected excitation, a double excitation in that. So, you know, this is a 2 by 2 diagonalization they need to do. Hopefully they can do that.
Hopefully, yes.
Yeah, well, yeah, I don't know. Well, it was noisy. If this was figure 6, yes. Those are the, it's that
It says hardware. So.
hardware, yeah, okay.
And they even have lithium hydride and HF in there in the figure 6 plot with hardware points. But like for HF, yeah, for lithium hydride, the depth is more than 10,000. It's like 20,000 or 42,000, depending on the basis. So I don't know how that is possible in hardware. I don't know what these points are.
I don't have a feeling of what is possible on hardware on a 11 qubit unerror corrected chapter iron machine. Thousands of bits.
No, you can do this a bit less than 1,000 to keep this.
Yeah, okay. And they're probably, yeah.
Like 26,000 seems doable. I don't know. Is that,
26,000.
yeah, that sounds like.
Yeah, but some of those could be single qubit gates or something, if it's just Adamad or something, but.
I'm exaggerating a bit, but it would take more than a week.
And T1 and T2 would probably not.
Wow.
So I'm not sure what these points are.
But it sounds like anyone can dial up the hardware via Amazon, apparently. AWS bracket.
Oh
Yeah,
yeah, yeah. Amazon is investing in that quite a lot.
I'm a bit confused by the whole workflow again.
Yeah.
So could you mind refreshing what they're actually exponentiating, what the linear system they're solving, and how they're getting the energy values out of that?
Yes, it did say in the supplementary information, it had how they calculate E core from this.
So yeah, I think the magic that they do here is actually explained by some of the modifications that they do to the algorithm. But Nathan, what part would you like to see exactly? The equation.
Big circuit diagram is probably sufficient, I imagine.
So that would be figure 3, I think.
Like a free. Go with that.
Yes, in figure 2.
Oh,
Figure 2, is that figure 2? That's 1. Figure 2.
3.
Let's have a look at 3, because that, yeah.
3 is the one that does these optimizations.
Oh,
Okay.
yeah.
Yeah, what any there is.
so yes, this is this matrix that is something to do with the Hamiltonian that we're not sure. The little h's, yeah.
It's not exponential.
It's not exponentiated, and it might be a similarity transform matrix. It just, inside the supplementary information, it just said,
Yeah,
yeah,
it's not really defined. Parts of the Hamiltonian itself.
yeah. The left-hand side, yeah.
Yes. So again, they refer us to section 1. TQ refers to the Qth cluster amplitude, while H refers to the amplitude of the Hamiltonian. Chi S denote the excitation functions constructed as follows.
So yeah, E-core looks just like the standard projected energy, give or take something.
That's figure 2, that's it, that. Equation 6 is figure 2.
Yes.
Is that the overlap is the left-hand side B.
Mm,
Just on the end.
And it is X, yeah, so, yeah.
Okay.
So, but the magic inside how they're applying that Hamiltonian is still a bit unclear.
Yeah, if it's defined in terms of cluster amplitudes, then
Yeah.
like what's the U in the GPE? I think that's the question.
Yeah, do they give any more details about how they actually create that unitary operation in the QPE, which is out of a non-unitary A? Yeah, I think that's the question. Yes.
Yes.
'Cause
So
A is non-unitary, but
or
QPE needs a U, doesn't it?
non-Hermitian at least.
Or is,
You need something Hermitian, so you exponentiate it. You get
so is U the exponential of the of A?
yes, that so in general, I'm just looking for one good representation that I had here. In general, U is just the simulation of the Hamiltonian via the exponentiation or any other simulation method that may be to your liking.
So it's some unitary Hamiltonian evolution. Somehow.
Yes.
Okay, with the A matrix.
Where
And that-
does the
yeah.
non-unitary part come into the algorithm?
That's in one of the modifications that we haven't discussed. Let me quickly find it. Sorry. Right. So they say that this operator may not be unitary, and it describes the excitations.
But as far as we can tell, then they shouldn't be exponentiating T here. Well, okay, when they linearize it, they get rid of E to the T, but there's still a Hamiltonian, which is not unitary. They have to do something with inside that QPE. And yeah,
Right.
is that, yeah,
The dimensions.
controlled unitary? Okay, never mind.
You mentioned something about Hermitian, right? So they take linear combinations of the excited states.
Interesting. Ooh. Verification. Okay. You swap some.
Right. So is that the section?
Then you QPE. Yeah.
That's not the.
Wondered why this thing called it.
I also object to the metallicizing of molecules. I suppose irrespective of whether or not the stuff they're doing is good to what they do for the calculations, the errors that come out seem quite big.
Yeah. I think, I mean, HSL, like, it's just, you can apply it to any problem that's solving linear set equations, right? But
Mhm.
you might not want to apply it to that problem. It depends on what the complexity is going to end up being. So do they kind of address that here, like why they think this is a good application of HHL?
Well, they say their argument is our results are not that bad, which is from 0. Something to up to 10% of accuracy. They also said that the advantage is that they do non-unitary stuff, which we haven't found. And what else? Yes, and the other thing is that they actually managed to run it on real hardware that maybe in the future will be better and more suited for this algorithm. So just for comparison, in the cryptographic applications that I'm using this algorithm for, people struggle with implementing anything above 5 qubits to get any sort of decent results.
As in classically or quantumly?
Quantumly.
Quantumly, okay.
And why is that?
Well, at some point, the equations that one would have to solve with this become too hard, or maybe they are not linear anymore. There are certain schemes where, for example, quadratic multivariate equations are used, and that's something that HHL struggles with. But our hope is that after some linearization or maybe some classical simplification, it would actually give some boost to the problems.
Because I guess the other thing is, aside from like the general application, when you're specifically applying it to a system, if the complexity depends on the square of the condition number, and this is so it's so it's a fairly strong dependence on your system, right? That you're trying to
Yes.
solve
In this
for.
very basic version that was published, I think in 2009, since then there've been some improvements that actually improved this complexity.
So I mean, loosely for a quantum chemical system, the condition number is at least proportional to the size of the system. Sort of. I mean, you've got to describe something, energy, which is an extensive quantity. So the bigger the system, the energy will scale linearly with that. And the condition number, in some way, feels like it should at least be scale with that. Rather than matrix. I mean, of course, if you project everything out of your matrix, you can get a really simple matrix, but you've already solved most of the problem then. So I'd say naive.
Yes,
Yeah,
and then
yeah,
you may not need it at all.
Yeah, you know, kappa goes at least as the size of the system, maybe far worse. I mean, at worst in a naive FCI, it goes as the system to the power of number of the number of electrons to the power of number of electrons. Is that right? No.
Right. I've got some
squared. Yeah. I think number of electrons and number of electrons, which is still not bad. N to the 4th log n as an algorithm is not horrible.
Yeah, you kind of lose any kind of I don't know.
Yeah. Okay, so maybe one of the difficulties here, if the problem they were solving, and we're still not entirely sure what that is, were solvable classically on the left, it should be cubic in the system size. Maybe. Oh no, n. No, oh god, n is horrible. N is the different n. N is the FCI n.
If you wanted like an exponential improvement, k would have to scale logarithmically or in n, right, or something like that.
Yeah, big N here is the factorial n, or at least is some power of the system size, because it's the size of your CI matrix, probably.
Okay.
Some matrix like that.
I think it scales. There are matrix inversion algorithms, which is the quantum singular Lie transform, which scale. So it's k log K over epsilon.
Okay.
Yeah,
Oh, that sounds quite a bit better,
yeah, I mean, that's similar to that.
Yeah.
I guess.
So yeah, it's just.
Oh, what's this?
Just from my notes, there was also a publication by this author, Ambanis, sorry for butchering it, that reduced this complexity on the condition number to something linear times polylogarithmic term. So it may not be as bad, but yeah.
There's a more efficient algorithm than that.
Yes, what I showed you here. What I showed you here is the classical, the original HHL circuit that I think was proposed in early 2000s. Since then, there have been improvements, and I can flag you to them. They pretty much speed up the algorithm by reducing this complexity on the condition number. Sometimes some memory improvements are made. Because obviously, and this is a huge caveat that maybe I should have stressed more vocally, to even start doing this problem, one needs to efficiently prepare, for example, B. And we just assumed here that there exists some unitary that outputs this states. And yeah, in general, the loading of the data is not trivial here.
So going back to your question, looking at this, is it going to actually make it into publication? It feels like it probably will, because it's doing something a bit novel. I'm not sure it's doing anything useful yet, but we don't need to worry too much about that. Yeah, exactly. I mean, probably don't, in terms of where they're sending it, if they don't send it to too many quantum chemists, it's probably okay.
So you say that the strategy is to publish in something not Nature, because quantum chemists do read Nature.
But they might review Nature, so that's okay.
Fair enough.
That's all a question of the reviewers. Yeah. I mean, I'm not sure it quite has a whizzy enough factor to say, yes, we've solved this problem enough to go to Nature, but it could make it certainly probably quantum or something. Yeah.
But one thing I find interesting is these kind of tricks they try to use to simplify HHL. Particularly, I caught my attention this thing about this multi-grid fixing for QP, which I don't fully understand. But it seems to be based on the fact that you know more or less how your eigenvalues are going to be for the A matrix. And I don't know if this could also be applied to only the phase estimation part of the algorithm.
I mean, in many quantum chemical things, we already know a really good guess of the answers. And so, yeah. But at that point, whatever their 2% precision was something that's a bit worrying, because you might even know the answer to 2% pen and paper or something like that. And it's those last 2% that matter in the correlation energy.
But I don't fully understand what's the limit in this precision. Is it because in HHL there is this problem where the precision is literally limited by the number of qubits you choose to represent your number, but it's binary.
I think the way to understand this precision, the trade-off between precision and the circuit size, is that they say, well, in 20 years we're going to have quantum computers that work fine for this sort of problems, compared to what we would be comfortable with using then. Let's say, 200 qubits or 100 or whatever. Now we offer 50% reduction at this cost of precision.
I hadn't fully appreciated, because in this case, they've got 5 qubits to represent the wave function, the B bit, and they've got 5 qubits to represent the binary string of the energy. And those 5 qubits give you whatever, not a lot of precision.
Not a lot.
Yeah, and okay. And is that where okay?
I don't know.
Yeah.
It must be a limitation there. And if you actually take 15 qubits to do it, your precision should be improving, I guess.
You might need to do a lot more work, I suppose. So yeah. So interesting. I mean, it's a neat way of putting a lot of things together, I think. We should start to wrap up in terms of time.
Yes.
Any last comments or questions?
I would try to repeat this algorithm with because you use the quantum singular value transform to do the matrix inversion by doing a function approximation on the
Inverse,
on the inverse function approximation on the operator, and then you don't have to worry about any of this binary string precision. The downside is you have to post select on the block encoding, and then there's also a matrix approximation error there as well, and you need to know the condition number one to get there to approximate the inverse function, or at least have an approximation to it.
But then how do you represent your answer?
The answer is still the answer is someone else's problem.
A PhD student or maybe an intern.
Yes.
So Leela, your question is completely unanswered as far as I can say.
Yes. Open research. Okay. Marcel, thank you very
Alex,
much.
I think Jet wants to say
I have
something.
a quick question.
Yeah.
So this is just a general HHL question because my chemistry knowledge, at least in this regard, is very small. So, I mean, I'm
So is
amazed that you
mine,
can even turn a chemistry problem like that into something that you could solve with a matrix equation inverter. But I was thinking, so HHL is a matrix inversion algorithm, and if you're trying to do this classically, a common approach is to block diagonalize. And I was just wondering if you're, just as a general HHL question, if you're aware of any attempts to improve sort of the functioning of HHL, or make it more effective or make it run faster by trying to block diagonalize, or choosing a particular basis so that you can
Yes. So the representation, this is a very good intuition. The representation of the matrix matters a lot, and different people are playing differently with it. For example, there is this approach of decomposing your target matrix into a sum of matrices with given sparsity that is tractable by the algorithm. I think there was also an attempt to adapt it to block diagonal matrices or something like that. I can look up the paper because I think I read it last week, something like that. So yeah, the intuition is absolutely correct, and yeah, playing with how the matrix look like, how the matrices look like is quite important here.
I think that's actually done in Harry's PhD thesis, as they applied the Schwarzschild transform to HHL.
Okay.
Yeah.
Oh well.
Cool question. Thank you.
Yeah.
Beaten by Harrow once again. Thank you for your talk.
Thank you.
Yeah.
Thank you all. It's very nice to stay in touch with Cambridge. Yeah.
Yeah. Excellent. And thank you for staying up late for us.
Thanks a lot.
Well, see you soon, I guess, in 2 weeks. Thank you very much for coming.
See you.
Thanks again.
No, it's quite novel.
Yes, yes.
It's interesting.
Yes.
I haven't seen a new album like that in a while.
Yeah. I'm just.
Let's say